And welcome back. As we continue looking at recursion, let's go ahead and use it to help us develop a new technique for sorting, which is that of binary search. So we're going to develop a recursive method that allows us to search an array to find out whether or not it contains a specified value. An array may contain a list of numbers, for example, let's say store reward cards that are no longer valid. And the clerk needs to search to see if the customer's card is valid or invalid. The indices of the array A are the integers 0 through final index. To make the task of sorting the array easier, we assume that the array is sorted. And this is one thing you're going to find when you look at binary search algorithms is they typically assume that you have a sorted array already. So because the array is sorted, we know that A of 0 has to be less than A of 1, which has to be less than A of 2, and so on and so forth, all the way up into the final index. In fact, this binary search algorithm, in fact, most binary search algorithms are going to operate under the assumption that the list that you're working with is going to be sorted in some manner. So let's look at searching the array. When searching an array, you're likely to want to know if both whether or not the value is in the array and where it's in the array. If you're searching, for example, that reward card number, then the array index may serve as a record number. Another array indexed by the same indices might hold something else, such as a phone number or other information used to report the suspicious card. Hence, if the sought-after value is in that array, we have our method return an index of where the sought-after value is located. If the value is not in the array, well, the array method would just return -1, which means it's just not in that bounding. So one thing to keep in mind, though, is our array may contain repeats, which is why we say an index, not the index. So let's actually start working on creating our algorithm. So we need an algorithm that's going to help us solve this task. Suppose the list of numbers is so long it takes a book to list them all. We have thousands upon thousands of numbers. If you're a clerk and are handed a reward card, you must check to see if it's on the list and hence if it's invalid. So how do you proceed with this task? Because you have this huge book, let's say it's got thousands of names in it. Well, first thing we're going to do, probably open that book to the middle and see if the number is there. All right, because we remember it's sorted, so we can look, all right, if it's in the middle of the book, let's see where it's at. So if it is not there in the middle of the book, and it's actually smaller than the middle value, well, we're going to work backward toward the beginning of the book. If the number is larger than the middle number, we're actually going to work our way toward the end of the book. So let's go ahead and develop the first version of our algorithm. So this idea of cutting things in half and then working through it is going to kind of give us an algorithm that works as following. So we have this variable mid that's going to be the approximate midpoint between 0 and the final index. And we're going to say if the key is equal to the mid value, well, we'll just return that. Else, if the key is less than the mid value, search A through of 0 through A of mid -1, because remember, it's less than that. Otherwise, we're going to do the opposite. So if it's greater than the mid value, search for A of mid +1 through the final index. You might have noticed that this looks kind of like a recursive algorithm. Because the search of the sorted list are smaller versions of the same task, we're designing an algorithm to perform, and this algorithm is naturally going to lend itself towards recursion. The small list can be searched with recursive calls to the algorithm itself. And our pseudocode as it stands right now is a bit too precise to easily be translated to Java code, and the problem with it right now has to do with recursive calls. There are two recursive calls shown. We have search A of 0 through A of mid -1, and search A of mid +1 through A of final index. So what we need here is some more parameters. So to implement these recursive calls, we need two more parameters because we have two distinct conditions. So a recursive call specifies that a subrange of the array is to be searched. In one case, the elements index 0 through mid -1. In the other case, it's mid +1 through the final index. So two extra parameters will specify the first and last indices of the search, so let's just call them first and last. Pretty easy to use. So let's go ahead and refine that algorithm. So using these parameters for the lowest and highest indices instead of 0 and final index, we can express the pseudocode more precisely as follows. So to search through A of first through A of last, we're going to do the following. We're going to say mid, of course, still that approximate midway point. And we're going to say if the key is equal to mid, return mid. If it is less than A of mid, well, return the result of searching A of first through A of mid +1. And otherwise, return the result of searching A of mid +1 through A of last. Now, with this algorithm, you'll notice that to search that entire array, the algorithm is executed with first set equal to 0, and last is going to be set equal to final index. The recursive calls we'll use other values for first and last. The first recursive call, of course, is going to set first equal to 0 and last equal to the calculated value mid minus 1. Now, of course, we need to look at our stopping case here. As with any other recursive algorithm, we must ensure that our algorithm ends rather than producing infinite recursion. If the sought after number is found in the list, then there is no recursive call, and the process terminates. But we need some way to detect when the number is not on the list, because up to this point, we're like, oh yeah, we found the mid number, great, but what if it's not in there? Well, on each recursive call, the value of first is increased or the value of last is decreased. If they ever pass each other, and the first actually becomes larger than the last, then we'll know that there's no more indices left to check, and the number is not in the array. So if we add this test, therefore, to our pseudocode, we can have a complete solution. So let's look at that pseudocode now for our binary search. So one of the things to kind of keep in mind is that we have this precondition that, it has to be a sorted array. And so we want to locate that key value. We're going to first say, if the first is greater than the last, this is our stopping case, return -1. Pretty much that it is not, found within the array. Otherwise, do the sorting, the searching that we have already talked about. Mid is the approximate midpoint. Key is equal to the middle value. Return it if it's less than that, if it's greater than that. And we look at this with a little bit of code here, and a little bit of algorithm with some kind of values that we can look at. We can start translating this algorithm actually into Java code. And this is going to be done in a method we're going to call search, which is an implementation of it. And how that method performs kind of looks right. You can see, for example, our key is 63. And so we have, of course, a list of numbers here. We're going to start at our midpoint here. And what it's going to do is say, okay, well, this is the midway point. It's not the midway. So we know that 63 has to be the number we're looking for. Is it in this half or this half? Well, it can't be in this half because that would be less than that. So it has to be in this half. So then we're going to narrow that half down. And you can see now we have two other stacks. And it's going to say, okay, it has to be either here or here. And of course, then we can find where that actual value is. So going back to designing the recursive methods, you'll notice that the method search solves a more general problem than the original task. Our goal was to design a method to search an entire array, yet technically this method will search any interval of the array by specifying the indices first and last. Now this is something that can be quite common when you start designing recursive methods. Frequently it's necessary to solve a more general problem to be able to express the recursive algorithm. In this case, we only want the answer case where the first and last are say equal to 0 and final index. However, the way our method is set up, the recursive calls will actually allow us to set them to values other than 0 and final index, which could be very useful. Now, before we wrap this up, let's of course check our recursive criteria. We want to make sure we have a good recursive method definition. First thing, of course, is there recursive? There's no infinite recursion. Each stopping case performs the correct action for that case. And for each of the cases that do involve recursion, if all the recursive calls perform the action correctly, then the entire case performs correctly. And sure enough, when we look at our algorithm that we've developed, yes, we have addressed each of these points. Particularly the last thing we had addressed, if we remember, was looking to see if we had a value that wasn't in the list, which would cause some infinite recursion. So the method search, of course, passes all of these tests. And let's go ahead and take a look at those examples of what that binary search actually looks like. So here we have a main program, which of course is creating a simple array here for us to have some values in. And of course, it's just saying, hey, here's the final index. We're just getting that right here. So that's position 9. We're saying, hey, the array contains what? It's just going to print out that array. And then we're going to then search for what we want that to be. It says for int key equals 3, key is less than 5, key plus plus. We're going to search that and see if it is either in the array or not the array. Of course, if we actually look at the algorithm itself, you can see right here, here's our recursion. We, of course, are pulling in first an array that we need to test. We are going to pull in what is the first value of that array we want to test, what is the last value, and what is the key that we want to actually search for. So in this case, we, of course, start with, int result is equal to 0. This is simply just something to keep the compiler happy here. And then, of course, we're going to do a test. And so this test, of course, is just going to look to see, this is, of course, at any point those two values exceed itself. And then here's the other half of the algorithm that we developed. we look to see where is that middle point. Well, we're just going to take first plus last and divide it by 2 because that would be the middle indice. And then we say, well, if key is equal to the middle point, well, that is the result. Let's go ahead and return that. Otherwise, we're going to call the appropriate recursive call. So if it's less than that, we'll call here. And notice it's mid -1. If it is a greater than, it's going to call here. So if we go ahead and run this program, we get the array contains, here's our list of numbers, and notice that when I printed these out, these were done with print statements. I could easily have made these into something else. Let's just actually do a tab here, just rerun that just so we can see that. It's a little bit nicer presentation. There we go. So the array contains 2, 0, 2, 4, etc. All right, and then it's going to test some values. It's starting, of course, here at -3. It says -3 is not in the array, -2 is not in the array, -1 is not. It says 0 is at index 1, because if we look here, 0. 1 is not in the array, 2 is in the array at index 2, 3 is not in the array, and 4 is in at index 3. So again, just a real cool algorithm that we can use to kind of start searching for things. And this is not simply limited to us using things like ints. We could have done this with strings as well to go ahead and start looking for particular things that might be. However, the big thing to remember with binary search is that it has to be sorted.